Here are the topics that we'll be briefly talking about in this pre-lecture video. So let's start with how to compute cross products. So to compute vector cross products between any two vectors, let's say you have some vector A crossed into vector B, to find the the cross product of two vectors is another vector. And as you may remember, all vectors have some direction and magnitude associated with them. To find the magnitude of that vector, what you do is you take the magnitude of A times the magnitude of B times the sine of the angle between the two vectors. So theta is the angle between A and B. So that's how you find its magnitude. And how you find the direction is using the right-hand rule. So you start your palm along A and you curl it towards B, and wherever your thumb points, that's the cross product of the two vectors. Now we're going to talk about how to take this cross product more in class, so if you're not quite sure yet, you're welcome to look up some YouTube videos that explain this nicely. We'll also talk about it in class. Now just this nice little picture helps you determine how to determine the direction of cross product for orthogonal unit vectors. So how to determine direction of cross product for orthogonal vectors. Also a reminder, orthogonal means perpendicular. So what are the orthogonal vectors that we're used to? In the XYZ axis, so X, Y, Z, we use the notation I hat for the unit vector that points along the X direction. We use J hat for the unit vector that points along the Y direction. And we use K hat for the unit vector that points along the Z direction. So what happens when you take the cross product of I times I with J? Well, these are both unit vectors, so you know the magnitude is going to be 1, but then what's the direction? You can use this little cyclic picture to help you determine the direction. So if you do something that's along X cross with something along Y, I cross J, well, if it follows the cycle, then you get a positive K. And if it doesn't follow the cycle, for example, if you do J cross I, meaning break the cycle, go the other way, then the answer is negative K. Next, what's J cross K? Okay, what's J cross K? Follows the cycle, it must be I. On the other hand, what's K cross J? What's K cross J? It breaks the cycle. It basically goes opposite to the cycle, so the answer must be negative I, and sure enough, it's negative I. All right, try these examples on your own, pause the video, and then we'll go over the answers. So what's J cross I? What's J cross I? Well, it's opposite to the cycle, so it must be negative K. So we start with negative K. Anytime you have some signs in the cross product, just ignore the sign first, find the answer, and then apply the sign. So what's basically negative I cross J hat? Well, I cross J goes along the cycle, so the answer must be K. So we have negative K hat is our final answer, because this minus sign just goes along for the ride. So even if you have just one of the vectors is negative, that minus sign can still be taken out. So K hat cross I hat with the minus sign on the outside. Well, K cross I goes with the cycle, so the answer is J. But since there's this additional minus sign on the outside, it's negative J hat. And we'll practice this in the homework and examples in class. Next, we want to talk about how to calculate angular momentum. Now, we're going to calculate angular momentum for some point-like objects. So let's say you have some kind of a point mass that is moving along a curve or moving in a circle. How do you find its angular momentum? Also, what is angular momentum? Angular momentum is the rotational analog equivalent of linear momentum. So just like we talked about, if you have a giant truck coming at you, how much oomph does it have? That was linear momentum. Well, what if you have a boulder rolling in place and you're trying to, or let's say you have a giant ball that is riding on some axis and it's spinning. How much angular oomph does it have? That's basically angular momentum. So angular momentum is a vector. It has a direction associated with it, and it's defined as a cross product between R cross P. For a point mass, R just points from the axis of rotation, whatever the point-like object is rotating about, to where the point mass is. So let's say I have some point mass here, and it's moving in this direction. Well, what is its angular momentum about the z-axis? Well, what we'd have to do is write down the vector r that points from the z-axis to where this particle is moving, and then we would cross product its linear momentum, which is basically mv, to figure out what it is. Now, going back to knowing, so just a reminder from a few slides ago, A cross B, the magnitude of it was AB sine beta. Beta is the angle between A and B. Well, the magnitude of R cross P is just, well, magnitude of R times magnitude of P, which is just M times V times sine of beta. So this came from magnitude of R times magnitude of P times sine of beta, where R is pointing, or how far are we from the rotation axis. P is linear momentum, which is mv, and then sine of the angle between them. So let's do an example of this for a point mass, and then we'll talk about extended bodies. So starting with a point mass, let's say we have a 2 kilogram mass is moving in a circular path of radius 3 meters in the counterclockwise direction with velocity of 4 meters per second. What is the magnitude of the angular momentum about the center of the circle? So there's a circle, here's the center of the circle, here's how the particle is moving, and we want to know what is its angular momentum about this axis in the center. Well, we're going to apply L for a point-like object is R cross P, whose magnitude is basically just R times M times V times sine beta, where beta is the angle between R and the velocity vector. So R for us, as a reminder, points from the axis to the object. So if I draw R, that's what R looks like. And then V is this velocity vector. Well, there's an angle of 90 degrees between these two vectors, so beta is going to be 90. So what do we get for this? Basically, we have R is 3 meters, M is 2 kilograms, V is 4 meters per second, sine of 90 degrees, and you get 24 kilograms meters squared per second. This is if you have a point-like object going in circles. What if we didn't have a point-like object? What if we had a whole disk that was spinning about the middle axis? What do you do for extended objects? Objects that aren't just point-like and rotating about some axis. So let's say you do have a disk. Well, what you do in that case is you take the moment of inertia and multiply it by the angular velocity of the thing that's spinning. So you would find the moment of inertia of this disk and multiply by how many radians per second is it spinning at, and that would tell you I. So let's do an example of that. So in this case, the extended object we're talking about is a uniform rod that's 2 meters long. So here's my uniform rod, 2 meters long, and 3 kilograms is rotating about one of its ends. So let's just say it's rotating about this end like this. So if we look from above, the picture looks like this. Here's my axis. We have this bar rotating at 5 radians per second. What's the magnitude of the angular momentum? Well, now we're going to use our formula for magnitude of angular momentum is I times omega. Basically, what's the moment of inertia? What's omega? Well, first we need to find the moment of inertia of this bar along one end. We go to our handy table and we find that the angular momentum of a bar about one of its ends, 1/3 ml squared. Then we plug this into this formula. We get 1/3 ml squared times omega, and we do this calculation and get 20 kilograms meters squared per second. All right, so that's some examples of how to calculate angular momentum. Now, what is the condition for conserving angular momentum? We're going to talk about how we get to this, but basically the time rate of change in angular momentum is exactly equal to the net torque applied to the system about some axis. And we learned on Thursday how to calculate torque about an axis. So if the torque about some axis, the net torque on a system is 0, well then dl dt would be 0 because net torque applied is 0. That means L is conserved. The angular momentum of that system would be conserved. Let's look at an example. So here, this is a preview to one of your quiz questions, actually, for the reading quiz. And the question says we have two buckets that are spinning around in a horizontal circle on a frictionless bearing. So they're spinning about this axis. Suddenly it starts to rain. As a result, what's going to happen? Well, first we ask ourselves, is the net torque 0 about our axis? So here's the axis, rain's falling down this way. Well, when rain falls down this way in here and hits the buckets, it doesn't apply any torque about this axis. There's some torque to turn the whole system like this or like this, but there's no torque turning it about this center axis. And there's no other forces acting on these buckets. No one's pushing this bucket into the board or out of the board or a page. So no torque around this axis. So we can say angular momentum is conserved. So if angular momentum is conserved, then we can say that the total angular momentum of this bucket system initially, before the rain falls in, and the total angular momentum afterwards as the rain is falling in should be the same. Well, I is the moment of inertia of this bucket plus bar system. So you can basically do mr squared for this bucket, mr squared for this bucket, add them up, and you get your initial moment of inertia. And it has some angular velocity it's spinning with. Well, after the rain falls in, the only thing that changes is the mass of this bucket and the mass of this bucket goes up. Well, if the mass goes up, you know if the final the final moment of inertia is also going to go up. If this goes up, what needs to happen to how fast it's spinning for the two sides to stay the same? Think about that when you're answering this question. And the last thing is, what are the conditions for static equilibrium? If you have some system, what does it mean for it to be in static equilibrium? Well, it means that that object should have no acceleration, meaning it should not be accelerating in any direction, and it should also have no angular acceleration, meaning there should be nothing causing it to spin about some axis. This is true if the net forces acting on the objects all sum up to 0, and the net torques about any axis of your choice has to also equal 0. If these two conditions hold, then we can say that the object is in static equilibrium, meaning the object is at rest and there's nothing that's going to cause it to move because there's no acceleration and no angular acceleration. All right, these are all the basics to the topics we're going to learn during week 8.